Okay, let's get started. Welcome back. And a couple of things that I would like to, announce before I start a lecture today. The first thing is that I apologize. Last time seems like the battery of the mic's not working, so the videotape without audio. So I would like to repeat some of the material, at least in a different way. So repeat a little bit of the last lecture. So those people who are taking this online, they can get it. And the second part is that Chancellor already asked more than once, all students should, on-campus student, undergrad should be taking class on campus in person. So there's no exception unless we have an episode, COVID episode. So please attend a class. The third one is that I call it 2A, 2B. Basically, Tuesday, the homework is always the computational one. So you turn in a paper copy on Tuesday lecture, summarize what you learned. And Thursday is the Google, like what you did submit today, is on the usually some definitions or visualization of certain reading material. And I try my best, make sure you can find it differently besides Wikipedia. Okay, so please just keep in mind, I'm using the paper copy to control the attendance because the school policy right now is we have to control the attendance. Okay, let's get started. So I'm going to repeat the Bernoulli process one more time. And this time I'm going to do it a little different so you can visualize it. First one is that we start with a clock. So the clock, I'll have time 0. Okay, so, and I'll have 1, 2, 3, 4. And if you can consider that this is a time step, it's 1 second, 1 hour, 1 minute, I don't care the unit, but it's 1, 2, 3, 4, 5. And then I'm creating totally 10,000 observations, start from time 0, okay? And so every time step from 0 to 9,999, I will use a probability statement. So you use a random number as a probability statement to generate a stochastic process. And once you have that, we'll have an event statement. There's an event or no event. And I still using the probability, but this time rather than greater than 0.7, I'm using less than 0.3 is 1, otherwise 0. So in other words, what is the probability to have an event? What's the probability to have an event is when you have 1, right? So how many times? Roughly should be 30% of the time. Agree? Right? So let's just do that. So totally I have that many events. And here, what I did is I can find 2 different ways to figure out how many event do I have. And here, since I'm just living, every time I change the number, it will change a little bit. So right now, you have 2 different ways to figure out how many events I have. 10,000, I have, well, roughly around 3,000 events. That makes sense, right? There's another way you can figure that out is using count if, okay? I'm just count if if from here to here, and then usually I can use 1 and said, oh, how many times equal to 1? So you can see count if or sum the 1. Both should be equal. Agree? And so if I have roughly 3,000 events, right? You can consider this. I have 3,000 So technically speaking, I should have how many, what I'm trying to say is that I have a milestone. If I have 10 milestone, I should have 9 interval from 0 to, so you can figure out how many times you have. 1, look at here, okay? I can have the waiting time on average is 3.33, or you can figure that out by doing this, equal to, okay? The total time is 9,999 divided by the number of events I have. Or I will say event I have minus 1. Okay? So I'm sorry, plus 1. Yeah, no problem. Yeah. I already said it. All students, grad students, on-campus students. Did you receive the announcement? Yeah. Per chancellor, this last 3 years, we said that, if for safety reason, if you don't want to be here, you can take it online. But now everybody should be on campus unless you register online. Okay. So roughly speaking, here this is the waiting time on average 3.32. See how I figured that out? Because I said total time clock is 0 to 999 divided by this. This is the time. Okay. The next things I did, okay, is if this is a number of event, this is event time. How you figure out the event time is using the clock time times the event. Okay, and so technically speaking, actually, this is a big trouble here because I immediately at time 0 I start. The minute I start, I already have 1 event. Okay, and if you don't want that to happen, you can say that, oh, I don't, the time 0, there's no event. I can only have time event after time 0. You guys follow me? You don't want to say that, oh, I have 1,000 soldier, and then at time 0, before the battle start, I already have 1 casualty. But this is just for you to think about when is your time 0, okay? But after that, it's just using event times, clock time, event times the clock. So watch here. Why 4 is, I have an event time, because 4 is 1 event, A is another event. So once you do this, okay, you will have the total number of event time. Okay, the total number of event time, and what I will do is I will copy and paste special value. So now I have all the event time here, but the reason I'm only copy the value because now if I sort it, okay, if I sort, no, just continue with the current sections. Okay, if I sort from the biggest time to the smallest time, now, so next I can use that to figure out my waiting time by using the last event minus previous event, last event minus previous event. Okay, and you do this, you will have the total number, total event time. And then here, I will check what's the maximum value. And why I want to know the maximum value, so I can, when I build a bin size, I can start from the biggest value. Okay, so here, the largest one is 22, so times 22. The next things you can do is this. Okay, use the total time minus the 0. Because if you use the total time minus the 0, okay, you will have the total number of event here. You guys follow me? Okay, because if I only count 0, that's no event, right? So if I count 10,000 minus all the 0, that's the total number of event. Okay, and then you can figure out the total time. Okay, you still can figure out that by sum them up together, because think about it. Waiting time, waiting time, waiting time, sometimes long time, sometimes short. But when you combine all the waiting time together, that is the total time. Now 9,999. Everybody agree? You guys can see why when I sum up all the waiting time together, it's the total time, right? Shouldn't be always the case. You know why? The last event could happen, for example, like right now, is a last event is very, very close. But look at here. In this case, our last event, it happened at 9,999, right? But if the last event happened at 9,098, then you will be a little shorter. But since we're using this for sampling, you can tell it's very, very close. And why you want to figure out the event time and the total number of event, so you can do it again by using this number minus this number. On average, the waiting time is 3.30 seconds. Okay? So far, so good? And remember, average 3.31 second. So you can turn around and say that using total time divided by this, you can know the average event. Okay, so far so good. Next, okay, once you have that, I'm using the maximum of the waiting time to build my bin size all the way down. You don't really need this negative part, but if I'm writing a macro for this, I will, keep the negative part. Doesn't matter. You won't use the negative part. Okay, and once you have this, you have the material to build your data analysis. So you do a data analysis, histogram. Hey, give me all the waiting time, and give me the bin size. From the largest to the smallest. Okay, and once you do that, you should have this done. And if I'm writing this using a macro, this is something I will do. We'll never have negative time, right? So I can delete that after I have this done. So now you have the waiting time and the total number of events. Let's do a double check, sum them up together. The number should be 10,000, but you know that only 0 means there's nothing, right? So after that, what will be the next step, young lady? Once I have the histogram, PDF percentage. Okay, yeah. and then CDF, right? I just wanted you to feel like we always follow the same procedure here, okay? So percentage, approximate the PDF, okay? And then I should have a CDF, cumulative done, and same thing. I will insert one here, so I can start from a 0 to build that. So for percentage, is every number minus the total number I have, divided by, okay. And CDF should equal to this one plus the increment. And when you're done, okay, and so we can now build the picture of the PDF and CDF using different approach. So first one look like this, okay, and second one is approximated, oops, like this. Something fishy. Oh. It's not right. Okay. Well, when something's bad and I couldn't figure out why, delete, redo it. Here we go. And I should turn this to this. And of course, the last one will be the transfer function from like a transfer function, and from here to here. Okay? Okay. Now let me do it using the other approach. The other approach, do I have the other approach? Oh, okay. The other approach, now we're doing it, is using a parameterized approach. The parameterized approach is based on a lecture note here, and is the, people ask me how come I don't have lecture note for week 2, because we're still using the material from week 1, okay? And is this, I'm really still in this area, okay? I'm trying to explain using the Poisson arrival process to exponential distribution. And before we deal with the math, we're trying to figure out how to do it manually. So the arrival process, here we're using this example because the CDF look like this. PDF of the exponential distributions look like this, and CDF look like this. And if you have the CDF, since CDF is from 0 to 1, monotonically increase. Let me repeat that one more time. CDF is monotonically increased from 0 to 1. So it's a transferable function. So in other words, is that if I have a function, okay, if I have a function look like this from nothing here from nothing to 1. So I can either figure out the probability, a random number 0 to 1 to figure out the count, or figure out the count to the probability. And I'll come back, repeat this one more time, but the relationship is that if exponential distribution CDF look like this, then if I know the probability, then I can basically treat this as your P. If you know your P, then 1 minus P equal to 1 minus exponential negative lambda x, then you can invert it back, knowing the P, this thing really is your x. Okay, so we're using these equations here. So how to do that? Okay, let me see if I can. I need to find a random number, and this random number is my P. So P equal to my random number. And remember, I have the clock is from 0 to 900. I have about what? 9,999 or 10,000 of them. For 10,000 of the opportunity or steps, what's the probability to have an event? It's 3%, right? So if I have roughly 10,000, I should have 1/3 of that. So how many events I should have is roughly, let's just say that, let's just use a number, 9,999 equal to times what? Times 0.3. Okay, I should have about roughly 3,000 events. So this is what I did here. I generate 3,000 random number. Okay? If I generate 3,000 random number, and I said, hey, I should have 3,000 waiting time. And so now, my waiting time equal to negative lambda is 0.3 log 1 minus p. Natural log 1 minus p. 1 divided by 0.3. Everybody agree with me? If you don't, let me see if I can write it differently. Okay. Let me. Okay. Okay. Remember, I need to have a parameter lambda, right? Right? Exponential distribution, I need to have a arrival rate, right? And remember, when we're using the counting process, when we did a simulation, how did I decide there's an event or no event? I said, if it's less than 0.3, hey, give me 1 hit. If it's more than 0.3, no hit. So I'm just using that as my arrival rate. So now I'm just saying that, okay, now I have a p, 1 minus p, natural log, negative, divided by 0.3. That's my waiting time. And I generate 3,000 of them. And once I generate 3,000 of them, I take the average. The average is about 3.38 seconds. I will have 1 event. And look at when we did the arrival rate approach. Where is that one? Oh, when we did a counting of that, if you go look at the waiting time, on average, 3.3 something. Okay? The only thing I did this time different from Tuesday is Tuesday, my clock is a much smaller clock. But today I just want to make it easier to visualize. Just say that, hey, my clock and my steps is exactly the same. Okay? 1, 2, 3, 4. So every step is one window to have an event. You guys follow me? Okay. And later on, if you don't like that, I can say that, every time step is half day. Every time step is 1 light year. Oh, sorry, light year is distance. Is any time window, okay? Okay, so if we do that, okay? Should be this one, right? Okay, so if I have this, I should doing the same thing, and people just watch here, okay? Since this is using an inverse function, so if I'm trying to match what I have using the counting process, I'm just saying that, give me the maximum number. Okay, give me the maximum number. Guess what will be the number? It's not an integer. But if I'm trying to approximate it, and I would like to have, 26, 25, 24. So what I did here is I will use a round up function and said, hey, run up to the next integer. And that way, I'll have the time step, 28, 26, 27, and so on. You guys follow me? So we can approximate a histogram using reasonable bin size. I heard Excel can do non-integer bin size, but I never done that, so I don't want to try it. Okay. Okay, if we do that, same thing, you can have, negative as long as there's no count for negative. So now what should we do? We'll do the same thing. Data analysis, histogram, but this time the histogram is from here to here, and the bin size is from, yeah, that's about right. Okay, if we do that, wrong place. Okay. You respond to what I did? Oh, good. So you are pay attention. Good. Okay, if we do that, now, Houston, we have a problem here. How come I don't have 0? Huh? That's mission impossible. Because you have, 3,000 of them, right? I would say that the highest one waiting time, the maximum, somewhere around 30 makes sense. Because 30 times 3,000 is about, I would say somewhere around 25 to 33. But I have a mistake here, so let me double check. Okay, let me redo it. Data analysis, histogram, from B2 to B, and from F2 to F37. Okay, now it makes sense. You should start from 0, and what should I do first? Sum them up, right? How many events should I have? Not as much as the 10,000. should be 3,000. I only simulate 3,000 event, right? So compare with the sampling arrival rate approach, what is missing? I should have 7,000 observation here from the non-event situation. But in this case, since this is 0, we just know it's big. How big depends on what you consider is your total number, okay? So after that, let's just for fun, to make it look like very similar to what we have before. Okay. We should have a PDF, approximation PDF based on the percentage. Okay. And you know that what is missing is you have a huge number missing. But if we just use the arrival rate as 7,000, that's how we did it. See, so I add 7,000 cases in. Start from B2. Now I have my 10,000 cases fake. Okay? People, you have problem or no problem here? Because we're using this equation only generate what? The event. The 0 we didn't generate, right? So if I want to approximate that with a function, that piece is missing, 7,000. But if I have that, then all I have to do right now is using this guy divided by 10,000. Huh? Yo. Yeah. Oh. I have no idea. Let's that's strange. Something to do with let's double check. Now I'm worried about the Let's play one trick to see if I can get rid of that problem, because I'm worried a bit too. Okay, let's do this. Control C, paste special, value, lock the value. Okay, and now let's shoot, they already changed again. Okay, let me do it one step at a time. Waiting time, and equal to max of this guy. It's 26, no, it's 27, and then round up. To 0. Huh? Oh, D is missing. Okay. Okay. But this time, I'm doing the same thing. Pay special value. Okay. Let's see if we do it this way. It's not gonna do anything strange. get rid of this guy? Okay. Let's first try, because I don't want to have too many manual steps. I prefer you guys can do this. This is already annoying, but I promise you, okay, once you visualize what's going on, later on, we're using SAS. In real life, nobody do it this way. Okay. Data analysis, histogram. And this time, I'm going to start from here all the way down. And from here to here. Hey, hey, hey. Bow. Okay. I know Excel, because of all those random number, it generates a lot of strange stuff. So whenever you need to do stuff like this, even when last semester I taught human factor and some of the biomechanical analysis, we did the same things. Whenever we collect the data, we paste the value. Otherwise, I don't know exactly why, but I know Excel doesn't like that kind of floating stuff. Okay, so to just make it look like, totally, I have 3,000 event and 7,000 non-event. So now I have this. The next PDF, CDF, you're gonna end up with the same things. Okay, so that's the first part of your homework due next Tuesday, and we already said it because of Monday is the holiday, so we're gonna do on Tuesday. You will try your best to approximate a PDF, a CDF, first using the event counting process, and the other one is we will try to figure out how to do it in a parameterized way. And when I did this last time, I also mentioned one more thing, it's about entropy, okay? And before, we just said that, what if I have an event, okay? Let's just say that, okay, if to have something is P and have nothing is Q, is 1 minus P, and we started by saying it's 0.1, so here it should be 1 minus 0.1, and this is the all the possible is equal to this guy plus 0.1, and you know that okay, and what I did is to show you about here I use 0.999 and here I use 0.001. You guys know that the fair coin is right in the middle, and based on the entropy computations, what is the entropy of a fair coin versus unfair coin? And the reason I don't want to use 0 and 1, because if you actually using 1, log 1 equal to 0, then you cannot do any more computation. But if you do it this way, then you can calculate, I usually just call it information of P. And what is the information of P is log 2 base 1 over that probability. Okay, and why 2 base? Because it's a binary system. Okay, and we can do information for Q. Okay, and we'll follow the same routine. And if you have them done, you basically said that the total amount of entropy, okay, or the total amount of uncertainty is, hey, how likely I can have this probability times the information or the log value versus how many times, if it's very unlikely to have P, then it's very, very likely to have Q. And how likely to have Q. And if you do this all the way, and you guys can see that you can build a histogram. Just look like this. Let me do it in a different way. Let me plot it. Insert. Huh? Oh. Okay. Why I'm doing this? I'm trying to show you that when you have the largest entropy, when you have a fair coin, okay? So when you have a fair coin in your Bernoulli process, 10,000 steps, okay? Everything's possible, then you don't know what to do, okay? But if I'm telling you that, oh, it's a coin very, very, very unlikely to have an event, so the P is equal to 0.00001, then what does that mean? Most of the time, nothing will happen. And if you know most of the time nothing will happen, in a reliability or survival analysis point of view, you know what to do, right? If I tell you that how likely you're gonna get hit passing the Craver Road, very, very unlikely when you walk pass by, because everybody stop and go. So how likely you will just go without even looking? Very, very likely. But on the other hand, if I tell you that, man, this is I-85, how likely you want to walk across that? You're going to get hit. Very, very likely. Then you're not going to cross. So the entropy of something, almost for sure. I can make this number even smaller, okay, and make this number extremely large, and you can tell how much information is carried by this, or how much information carried by certain, almost 1. Log of 1 is almost 0. If I tell you sun gonna come out from the east next day, what's the probability? 100%, right? Who cares? So you don't carry any uncertainty. When you carry a lot of uncertainty, 50-50. So if I want to play any game or do anything, like, there are 3 things people like to talk about, right? Try to predict weather, stock market, or elections. There are a lot of uncertainty. Then you know that if you have certain informations, that will make the big differences, okay? And this is not the class we're doing it. In Bayesian class, we actually try to figure out how to reduce the entropy. But in this class, we only talk about, hey, what's the shape of your distribution? And generally speaking, we don't like uniform. Uniform means everything equal opportunity. Everything could happen. We like to have something either not gonna happen or something gonna happen. But on the other hand, people, would you like to work on a jobs that absolutely something bad gonna happen, or absolutely for an engineer, you don't want to work on those two situations either because they don't need you. It's somewhere in between there. Yeah.
So if there's two possibilities in like section C, will the max entropy always be 1?
For probability,
If there's only two outcomes.
yeah, 50-50. Yeah. So
You know two possibilities, but they're not equally likely. If they are equally likely,
okay, and for your questions, let me show you something else. Okay, so let's just do it this way. Okay, say I have four possibility, then I have 0.25, 0.25, 0.25, right? So if I have 0.25, 0.25, 0.25, now let me do it the opposite way, because that way you can see it easily. So that's the probability, 0.25, 0.25, 0.25, and then what will be the entropy, the information carried by that is log 1 over that probability, take 2 base. And so now if you try to calculate the total entropy is some product of upstairs, downstairs, right? And why this times 2? Because technically speaking, I'm almost like flipping 2 coins. But so we know that this is my max right now, and all you need to do is do this, okay? I just make this guy's really, really big. One side really, really big. Let's just say that I make it 0.7, okay? And then I'll make this guy's equal to this guy times 30%, and another 30%, and 30%, 0.3, and then this is equal to 1 minus the sum of this guy, the first 3. No, should be, okay, fine. Okay, and, you know, we can double check. The probability should equal to sum of this 4 options equal to 1, and this equal to 1. But look at it, the entropy here is 2, and the entropy here is less than 2. Why? Because if I ask you to bet on something, say I have A, B, C, D, 4 opportunity. This is 4 candidates for our next state elections, or is it easy to figure out who's going to win? Very easy, because this is 0.7, okay? And I can make it even easier. Make it 0.9. Okay, let me do it this way. So this time, make it 0.8. If I make it 0.8, okay, do you think the entropy will drop even more? Let's try. Oop. Oh, I got a negative. So here I need to play 20% maybe. And here is 20%. Do I have leftover? Yeah, I have leftover. Huh? Okay. See, drop even more. So from a deeper computational view about the world, okay? we all talk about smart cities, smart transportation, smart. Whenever people try to make things smart, right? Right. How to like YouTube right now is very smart. When they transfer the file, they know how to compress the file. And how did they figure stuff like that out? They already figure out that something is very consistent. They can allocate very, very little resources. A lot of uncertainty, they need to allocate more resources. And whenever they try to allocate resources, they did an entropy accounting. They try to figure out, oh, how can I allocate a computational resources, transmission resources, any so-called smart stuff. When they do the data mining, machine learning, what they're really trying to figure out is that where the uncertainty coming from, okay? That is beyond the scope what I would like to cover this semester for survival analysis. But since we're talking about probability, I have to let you visualize how entropy is used, okay? And this is the homework that I asked Victoria help me to put in on Tuesday. Nothing changed. You're still doing the same things, but I just repeat that one more time so you guys can visualize it, okay? So far, so good? Okay, so now let's go back to our lecture notes, okay? The part that is missing is, I already said it, okay? If I have a Bernoulli process, a so-called Bernoulli process, really just flipping a coin. And you have a P x time, total n minus x time for Q. And so when I say this Bernoulli process, I really did not assign which one I should have P, which one I should have Q. But if I have this PPQQ and start saying that, okay, for n of them, n time steps, n slot to do this PPQQ things, pick x of them. So you have a combinatorics upfront about your PPQQ. So whenever you have the combinatoric Cn take x combined with your Bernoulli trial, flipping coin, this is what they call binomial distribution. And whenever you talk about binomial distribution and you start saying that, hey, I would like to approximate that opportunity by saying that, okay, let me sample 10,000 times. If I have 3,000 times, okay, and then whenever you're using a number to approximate that, and then when the n getting bigger and bigger, and when you get n getting bigger and bigger, then this estimation becomes stabilized. Okay, we call this stabilized binomial distribution. We give a special name. It's called Poisson distribution. And Poisson distribution is very, very useful because once I have the Poisson distribution about the arrival rate, about the event, then the interval between the two events is what we call the waiting time. That is the starting point of your queuing theory, okay? And I did not ask you to do this in today's exercise. One of the system engineering for graduate school, a lot of time is called queuing network. And queuing network basically, how to assign for your telephone using different antenna for communications, using satellite. And queuing network basically is let all the electronics have a priority, wait, and serve. And to do that, all the queuing network, you have to start by learning Poisson distribution. So Poisson is very, very useful. And why a survival class will also talk about a queuing theory is because we're using this as our starting point for our survival analysis. Like the Excel example I give you, you can consider that I'm walking with another 99 soldiers, okay? Moving from time zero, time zero, how many survival? 100, total number of soldiers, or 1,000, total number of soldiers. And then we move forward. Step one, each one of us in that line got an opportunity to get shot by the enemy. So the survival rate we count how many survive after one step, and then we move to the next step, how many survive, and then how many survive. So every time when some of the soldier, some casualty happened, you can consider this bullet is the COVID virus hitting a bunch of students in the case, then we wait till something happened. This time is the casualty. Then it's a survival analysis. If I'm talking about satellites hit by the solar wind, how many satellites can survive after a solar event? That's also about how long, start from time 0, time 1, time 2, and that's the reason why we take advantage of Poisson distribution. Now, to learn this Poisson distributions, you just need to remember, and I'm not a mathematician, okay, so I don't like proof, but this one you need to kind of visualize it, because this thing is so useful. It's kind of the starting point of a lot of other stuff. You just need to remember combinatorics is n takes x, so become n factorial, x factorial, n minus x factorial. P becomes lambda over n, Q becomes 1 minus lambda over n, x number n minus x, and then break the things into 3 pieces, except that keep the x factorial and the lambda x alive. And so the par here is n to the n factorial, and here is n minus x factorial, so upstairs I have n minus 1 to n minus x plus 1, and total here, denominator is n to the x, and down here I break the last piece into part 2 and part 3, okay? I will tell you this, okay? If you want to apply for grad school, especially you want to do, we have some students, especially undergrad students, senior year, some of them say, oh, I want to go to Northwestern, I want to go to some very competitive grad school, and a lot of time there are interview questions, and do you understand how you turn a Poisson distribution into an exponential distribution? You need to talk about something like this, okay? Okay, if I have these 3 pieces, and then for each one of the pieces, the first part, I can break them down. N divided by n is equal to 1. N minus 1 divided by n become 1 minus n minus 1. And then every piece, when n is very, very big, this become 1 minus 0, 1 minus 0. So a bunch of 1 minus 0 become products of 1. Next, the second piece, this turned into your Cal 1 or Cal, should be a Cal 1. 1 to the exponential power of negative lambda. And then the third piece is, again, everything is divided by n become very, very big, become 1 minus 0, 1 minus 0, and a bunch of 1 minus 0 is 1. So 1 to the power of whatever is 1. So this whole thing, when n getting really, really big, this equation become Poisson distribution, okay? And if I have this equation, write it down as a Poisson distribution, remember, my previous time steps, what I have is what? It's 1, 1, 1, 1, 1. But now I can say that, hey, maybe the window is very big or very small. The W is, a month, a week, a 1 millisecond, 1 microsecond. So the W could be big, could be small. But all I care about is that if I consider that the window is so small, I only allow one event to happen, then every time I can only have one event to happen, that means what? No event to happen means that either there's nothing between 0 and W, then n is equal to 0, and you can rewrite this equations becomes 1 minus exponential lambda times W, lambda times W, okay? Lambda is my arrival rate, W is my window, and n to the equal to 0, this term becomes 0, 0 factorial becomes 0, so this whole thing becomes 1 minus exponential negative lambda, how long the window gonna be. So we turn the Poisson, hey, when is the next thing's coming to the question in exponential is how long I have to wait until something happen. Okay, so we turn from a discrete distribution to a continuous distribution. Okay, and continuously, if this is my equation for my CDF, take the derivative, this is my PDF. And if this is my CDF, I can say this is P, then I can invert that into the what do you call that things? The random number for waiting time. Okay. Everybody, I'll give you one more time, 1 minute to look at these two slides. Okay, if you remember, you should have this at least once in ARENA, one time in OR1 in queuing theory, maybe one more time in probability and statistics. Everybody should seen this more than once, right? Okay. And of course, the next things you want to talk about is exponential distribution. Okay, the expected value is 1 over lambda, and variance is 1 over lambda squared, or standard deviation equal to the equal to the mean value. Okay, and think about it this way. Okay, why exponential distribution is memoryless? The variation doesn't change. The expected value doesn't change. They're equal no matter where you are. And so, if I'm talking about survival analysis, the light bulb, okay, the expected total time, say, is 3,000 hours. The variation is 3,000 hours. Okay, I'm having a light bulb, 3,000 hours with 3,000 hours of variations. That's not good to figure out, right? But guess what's even worse? If I tell you that I give you a light bulb, this light bulb already burned 10,000 hours, and I give you another light bulb, is only burn 300 hours. Okay? But if I ask you, so what's the difference between their expected value and standard deviation? Given the history, one already burned for a long time, the other one never burned, guess what will be the difference? No difference. I don't care how many times you use this. If I give you an electronic piece or I give you a watch, and I said that, oh, this thing's the survival rate or the reliability is exponentially distributed, you know what it means? Use one and the brand new one are exactly the same. Okay? So, do you think there anything like that in real life? Probably not. People said Rolex watch, somewhat like that. I don't know. Okay, but on the other hand, later on, we will start saying that. But in real life, nothing is memoryless. And guess what will happen to a lot of company? Okay, especially in the 80s, the big three car company, they'll give their employee, Chrysler GM will give their employee brand new car to drive home. You know why they do that? It's called pre-burn. They say, oh, we're going to sample if this car is good or bad so our employee can give us some feedback. On the other hand, what they really did is they realized that when their reliability is not good, guess when usually the car break down? At the very, very beginning of the first 100 days or 100 hours. So you don't trust those things, right? So I give it to you so you can bring it home, play for a while, pre-burn. So if it's break down at home. Then you can fix it. After 100 hours or 1,000 hours, the pre-burn period, they bring back to the factory, polish, clean up everything, and then reset the odometer and push it out. So pre-burn sometimes is a good way to handle something bad, okay? And I'm originally from Taiwan. I grew up in Taiwan. Almost done. After this story, I'll let you go, okay? In the old days, they said that when they have kids, they don't give them a formal name. So they usually give baby a nickname, It's almost like, big dog, little eagle, something very unofficial. Why? Because most of the people there, they don't know how to give a formal name to their kids. They need to go talk to the scholar. And they don't want to pay the visit until they know the baby survives, say, 1 year. Because infant fatality rates very, very high in the old days. And so the first year, they don't want to waste a good name, a scholar name. They will pre-burn the hours until they know, hey, is this baby going to survive? Then they go ask for a name. So I consider that as a baby pre-burn policy. Whenever you have a pre-burn policy, most likely it's not memoryless. Okay, have a nice long holiday. See you next Tuesday. Okay, have fun.